Welcome to a new section. We're going to talk about the change of variables in double and triple integrals. Okay, this is gonna be a long section because there's a lot of new ideas that we have to tackle. So let's start off with our goal. What's the goal here? Well, we're gonna start off with the double or triple integral, and we'd like to make it easier to evaluate using the technique that we call change of variables. Okay, so when was the first time you saw a technique like this? Well, the first time you saw it was when you were learning integration, and we called that technique U substitution, because the idea was we introduce a new symbol U to replace, so in this case, we would have like an inside function g of x, and then we would write symbolically du is g prime of x dx. And the idea here is if we started off with an integral in x that had a very special form, right? So we had to have f composed of g times g prime dx. Well, under these situations, we can change variables to the variable u, where the goal here is, well, can you figure out what function to take the integral of? Can you find the antiderivative of f of u? The idea here being just kind of simplify it, and the mechanisms are of the change of variables formula is essentially the chain rule version. Okay, so there's kind of two types of substitutions that we can encounter here. Um, the U substitution goes by the name of a push forward, and there's another type of substitution called a pullback. So if you remember, U sub looks very different than trig sub. Okay, so usually push forwards, think of these as the U substitution, and then pullbacks, think of these as trig substitutions. Okay, we'll talk about this kind of formalism at the very end, but the idea is we'd like to generalize U sub to higher dimensions. Okay, and secretly we've already seen these how this works. So when we introduced polar coordinates earlier in the chapter, okay, we saw how to do double integrals here, and we remember that there was formulas that told us dA in rectangular coordinates is dx dy, but when we switch to a new coordinate system, this is r dr d theta. Okay, and then when we learned cylindrical coordinates, this is in three variables, we would say, okay, in this case, since we're integrating volumes, we would look at the differential form dv, which is dx dy dz. And for cylindrical coordinates, the way to remember it is polar plus z, so r dr d theta dz. Okay, and then finally, our third type of substitution we learned was spherical coordinates. Okay, also in three dimensions. So this one had the most interesting form here, where dx dy dz, when we changed the variables to spherical, we had rho squared sine of phi times d rho d theta d phi. Okay, and we gave explanations for where the r and the rho squared sine of phi comes from in each thing, but there were more geometric heuristic explanations. So in this section at the very end, we'll revisit these and prove them rigorously. Okay, so a few more things before we continue is just this section is indeed difficult. It's probably the most conceptually difficult section we've covered so far. Why is it so difficult? Well, it's a super fundamental result, so there's a lot of ideas going on here. But the other thing that makes it challenging is most of you haven't taken linear algebra yet, but secretly there's a lot of linear algebra behind the scenes to kind of do this right. Okay, so just learn your linear algebra, kids, is the lesson here. All right, let's start off with talking about the geometry of maps from R2 to R2. Okay, so what are we going to do here? We're going to start in the x and y coordinates, and we want to switch to new coordinates, which I'm going to call u and v. Okay, so we start with two old coordinates and we change to two new coordinates. the notation we're going to set up here is we're going to say, okay, D is some region in the plane, but we are going to label this region using X and Y. Okay, this is D, that kind of peanut shape. And we're going to think of this as in the XY plane. But then we're going to have another region called D star, also in the plane, but we're going to think of this as a completely separate plane. So I'm going to draw it separately, okay? And this is going to be in what we're going to call the UV plane. Now, looking at this image here, obviously I drew D star to look easier, okay, from the point of view of, that looks like a circle. And why are we doing this? Remember, it's going to make the double integral easier / possible, okay? So remember, we saw in polar coordinates that we would integrate some things where we just couldn't do it in X and Y. The moment we switched it to polar, the fact that we got that extra R allowed us to integrate it with substitution. Okay, so that's kind of why we are doing this. Okay, and then the original variables, this would be either impossible or quite difficult to compute. All right, so the idea here, more notation, I'm so sorry, we have a lot of notation in this section. We're going to say D is TD star, because we've got this map here. Okay, you can see I've written it in arrows. I've got T going from left to right, but I've also got its inverse transformation where we go from right to left. Okay, it's inverse in the following sense, right? So you've seen something like this before. If you remember pre-calculus, if you've got a function and its inverse, if you do function composition, what is this, right? So first you do f of x on the inside, and then you do f inverse of x to that, and it brings you back to x, right? So the idea is if I start here, go to this point, but then go backwards, I'm back to where I started. Okay, this is the higher dimensional version, and if you remember inverses, I can do these compositions in either order. Okay, so in the language of linear algebra, we would say things like T composed with T inverse applied to the point, let's see, T eats a point in the UV plane. And if I do T and then I follow that with T inverse, I'll basically land back at the original input U comma V. All right, so that's essentially the functions point of view here. And again, these are new functions that we've looked at, that we are looking at. And again, when we use this word map here to denote the fact that we're doing something slightly different. Okay, so D is, we would say that D is the image. Under T, the transformation of D star. Okay, and that's essentially what this notation suggests here, which is suggested in the pictures. Okay, now the key question is, we want to essentially figure out what happens to areas, right? We've got the area of that kind of peanut shape in blue. How does that relate to the area of D star? Okay, clearly you can see that whatever this shape is, it's different shape, potentially different size than this thing over here. Okay, so there's probably some sort of number that we have to multiply right here so that we can basically, again, we don't distort any of the areas when we do a change of variables. So we call this thing a distortion factor, okay? And more simply, instead of just doing it at the level of the entire set, what if we do it at the level of just these little tiny rectangles? Okay, so that's the idea here. All right, so what we need is this transformation T that sends points from R2 to R2, okay, and these go by many names. So one name is called the coordinate transformation. Okay, another is a differentiable function. And if you're kind of keeping track, we've got a differentiable function of two variables. And because we've got two variables as the output, so we can actually call this a vector valued function of two variables. Okay, but those are super long, so I think it's much nicer, and I prefer just saying mapping, okay, where the idea is this is just a function, a generalized function, where it eats two numbers and then gives us two numbers. Okay, so the idea here is I can split up the effects of this transformation via these brand new equations here. Okay, I find it really helpful to actually start with this kind of box part here where we have t. What does t do? T is going to eat a point in the UV plane. Okay, and we're going to use vector notation here. It's going to get sent to a vector in the xy plane. And the idea here is our x and our y are dependent on these brand new variables u and v. Okay, and I don't think I need this notation in our section, but just, in case you're curious, we can use much more compact notation using vector notation here, and that's going to generalize to even higher dimensions when you take future courses. Okay, here's a good time to just pause, just kind of read this last little sentence here, see if you can pause the video, fill in the blanks, just to kind of make sure you understand the key terms here. Okay, so let's talk about t. T, it sends a point where? So where do we start with t? We start in the UV plane, and it sends it to a point in the xy plane. Okay, again, t goes in that direction. What about t inverse? Well, it reverses it. It starts in the xy plane and then sends something to the UV plane. Okay, cool, and we call this the inverse map or the inverse transformation. Okay, great. So a little bit of the fine print here. So technically, in order to make all of this work, we need two technical restrictions. We need to make sure that the functions are one-to-one. So we call those also injective transformations. We also make sure that t is onto, also called surjective. Okay, just a quick recap. You hopefully saw these terms in pre-calculus. So 1-1 just is my brief abbreviation for one-to-one. So what this means is if you've got two different inputs, x and y, and they're, x1, x2, and they're not the same, then what you're going to get is two different outputs. Okay, onto means that every y value there is an x so that y equals f of x. Okay, let me just translate these into more geometric conditions, or let me just give you two examples. So one-to-one is a function like this. So one-to-one means if I've got two different x values, I've got two different y values. What that translates to is it passes the horizontal line test. Okay, and this is one-to-one check mark. However, it's not onto. Why? Well, because all of the negative y values aren't targeted by this function, right? So only the positive, or let's say only the non-negative y values are actually hit by the square root function. Okay, so let me give you an example briefly of a function that is both one-to-one and onto. Okay, a good example of this would be x cubed. Okay, when you look at x cubed, it clearly passes the horizontal line test. All horizontal lines pass the graph of the function once. And it also is onto in that if you imagine sliding the horizontal line up and down, every single y value would eventually be targeted by a single by some x value. So this would be one-to-one check onto check. Okay, now what this does is, first of all, it's the technical requirement so that the T inverse exists. But the way to really kind of convince yourself why we need this is this danger curve here. What is the warning? We'll make sure that we do not double count. Okay, so what we risk is, like for example, if let's say we've got a disk in polar, okay, typically we use the range of values of 0 to 2 pi for theta, but what if we did something like 0 to 4 pi? One way to think about it is essentially I am double counting that disk, okay? So, and this is something that we don't want to do, so we just want to count it once. So that's what, these are the two conditions so that we can guarantee that. Okay. So just keep in mind here that, right, D is in the blue XY space, and then D star is in the U and V plane. Okay, the main thing about this little fine print here is in our class, you can assume that the boundary curves are sent to boundary curves. Okay, so this is the important thing that I'm going to reference. Okay, and the restrictions are the types of transformations we have to consider. As long as they have these requirements, it satisfies this property. Okay, let's take a look at linear maps versus nonlinear maps. Number one, there's an entire course called linear algebra, probably the next course you're going to take, that is devoted to the study of linear maps, matrices, and basically higher dimensional vector spaces, called Math 260. And essentially, if you're going to want to basically figure out multivariable calculus with more variables than just 2 and 3, you fundamentally need linear algebra, because linear algebra, as we'll kind of get a taste of, is linear maps are essentially the higher dimensional versions of a straight line, right? So, and remember, the tangent line was very important in Calc 1. We looked at tangent planes, okay, and we didn't use the language of linear maps, but to do this in higher dimensions, you fundamentally need this language. Okay, what else? So what's calculus? So just generally, right? What is calculus all about? Well, we try to study curvy things, right? Because we know how to study linear things very, very well. Well, we approximate curvy things with the straight stuff. Okay, so this is why calculus and linear algebra need to be able to talk to each other. All right, let's look at some very easy but informative examples that I hope you appreciate, and this is going to build the intuition for how to think about these objects. Okay, so let's start off with this example. Let me box it here. So T is a transformation from R2 to R2. So we eat two variables U and V, and we get two variables. Okay, and remember, what do we call these? So we're going to call this thing X, this coordinate Y. So basically, these are exactly the equations that the transformation defines. Okay, and what do we mean by a linear map? Well, the easy explanation is look at the functions. They're only linear in U and V in the sense that the exponents that show up are just power 1. Okay, technically there's a few more things, like I've got that little note in gray. It sends also 0 to 0. Okay, so what is going to be D star? So D star, we want to make that the unit square in the UV plane, so we know how to draw that. That is going to be the following square. We're going to call that D star. Okay, and this is actually something that I want to also add to this picture here. I'm going to draw a little bit more. Okay, I'm going to draw a little smiley face with a nose. Okay, because the linear maps, right, when we start with this box, they actually encode a lot more information than just where the points get sent to. But let me just work out this example, okay? And remember, this is our notation here. D is in the blue, okay? What happens when we look at all of these points? Where do these get sent to? So one way to think about it is, let's just look at the corners. And we can actually just start plugging in the coordinates, okay? And in fact, you should pause the video and just convince yourself of what I'm going to say in the next part. So if I put 0, 0 for u and v, put them into this transformation, well, I'll get 0, 0. If I plug in 1, 0, I'm going to get 3, 0. Okay, and similarly, you can kind of see if I plug in 0, 1, I'll get 0, 2. And if I plug in 1, 1, I'll get 3, 2. Okay, now the other part we should convince ourselves is, well, if I look at that curve right there, what curve is that? That curve is v equals 0. Let's try to do that fancy erase trick. Didn't work. Well, if v is equal to 0, what is the range of values that you see in the picture for u? Well, the u goes from 0 to 1. Okay, and then looking at this transformation right here, right? If u goes from 0 to 1, then x is going to go from 0 to 3. This is going to give us this curve right here. Okay, oops. Of course, now that erase trick works. Okay, and notice that in the xy plane, what is this? This is going to be just, it gets sent to y equals 0. Okay, well, you can kind of just check that all of the boundary curves get sent to all of the boundary curves in a similar fashion. And again, this example is pretty easy, so I'm not going to do all of the details here. So what we're going to get is we're going to get this stretched rectangle. So what happens to the face? Okay, the idea is this transformation is telling us stretch the x coordinates compared to u, stretch them by 3, and stretch the y coordinates by 2. So I'm going to draw a smiley face here to take into effect that they're stretched, right? So the eyes get kind of wider. Technically, they're getting wider and longer. The nose is going to be wider and kind of stretched out a little bit too. So we get, some sort of face that looks like this. If you have ever seen Silly Putty, and if you are fortunate enough to actually hold physical newspapers, when I was a kid, we would take Silly Putty and put it on a newspaper, and then when you stretch the Silly Putty, you can see the letters on the newspaper stretch out. So this example reminds me of that. Okay, and one more piece. Let me just draw a little arrow here to kind of remind me, since we were given t, we go from here to here. Now, here's the key idea. How are the areas distorting? Well, if we start off with a unit square, we basically start off with the area on the left. Area is 1. Well, how many squares do I need in the xy plane? Well, I need, let's count. 1, 2, 3, 4, 5, 6 of them. Okay, so essentially I need 6 unit squares of the uv to basically make up a dx dy. Okay, so you might be thinking, well, a dx dy is, still a square, but the idea here is the transformations are telling us to transform the unit square into basically 6 copies of it. Okay, so we're going to call this 6 here a distortion factor. So I like calling it that. Okay, and it's the transformation t that's telling us how to distort. Okay, cool. Now, let me show you something interesting here. So remember, we looked at determinants when we introduce cross products. And let me see how much I can zoom in here. I want us to look at the following. I've got the determinant of the following, and these are partial derivatives. Okay, keep in mind that x and y are the coordinates of this transformation. Those are just functions of u and v, so I can take partial derivatives with respect to u and v. So what is x? The partial derivative of x with respect to u is just 3. Partial derivative of x with respect to v is 0, because there's no v's there. Okay, similarly, the partial derivative of y with respect to u is 0, and the partial derivative of y with respect to v is 2. So remember how determinants work. Determinants work where we multiply the diagonal and then subtract the off diagonal. Okay, so we end up doing 3 times 2 minus 0 times 0, and this gives us 6, which is curious that we have exactly the correct distortion factor, right? So we've got kind of 2 ways of arriving at it. Okay, so the other thing that's kind of interesting is basically this distortion factor of 6 is everywhere in the plane, right? If I took, I don't know, this little cat over here, I don't know if this is going to work, but let me try it. First, let me move it over here. Let me color it blue. Okay, and this is, don't take this too literal, please. But what I have to try to do here is resize it and make it 6 times as big. Okay, something like that. Okay, that's working everywhere, not just for the unit square. All right, cool. Let's look at the next transformation. So the next transformation is another transformation from R2 to R2. I'm giving you the following formulas. Okay, and I've got here a little note that this is a non-linear transformation. So what makes it non-linear? Well, the cosine and the sine are not linear functions of v. Okay, so I won't prove that. I won't explain in more details, but basically linear functions, all I'm allowed to do is add basically a constant multiple of one variable, a constant multiple of the other variable. That's all I'm allowed to do, and cosine is not that. Okay, so I'll come back to that light bulb key idea in a second, but let's start with what is this? Well, remember this is going to be our x, this is going to be our y, telling us our new transformations. So what is d star? Well, I want us to look at the following. So in this Cartesian product notation, remember that when you see this, what I'm telling you is I'm telling you a range of values for u. U is going to go from 1 to 2, and v is going to go from 0 to pi over 4. Okay, so in the UV plane, what I've got is the following. So if I look at all of the u's equals 1, I've got a vertical line here. And if I look at all of the u's equals 2, I've got another vertical line. And if I look at just the u's, I would get basically this infinite strip. Okay. What about v's? Well, v's go from 0 to pi over 4. So what is pi over 4? Pi is about 3 divided by 4, so it's about, so not drawn to scale here, a little less than 1. So I will just put it over here. Okay, and then same comment about v's, right? V's are going from 0, so that's going to be the u-axis, and then to pi over 4. Okay, so what we get is I am going to get this rectangle. And let me draw it thicker. I've got basically 4 sides right here of the rectangle, and this is what we're going to call d star. Okay, well, what is going to be d? Okay, we know what t is, so I've got the little arrow here. Well, this is going to take a little bit of work, but let's go ahead and do it. Again, ignore the fact that, ignore this key idea here. I want us to do it from essentially first principles. So I've got these equations. X is u cosine of v. Y is u sine of v. Okay, and essentially, let me just take two of the curves, and then you can kind of see what the general process is going to look like. What curve is this? Well, this is the curve v equals 0. Okay, and the range of values for v equals 0 that I'm going to look at are u goes from 1 to 2. Okay, so that's going to be one piece. And what's the other one I want to look at? The other one will be, let's look at this one. What is the range of values? Well, this time the v's are varying up and down. V goes from 0 to pi over 4. But what is constant is that u equals 2. Okay, so let me highlight just kind of the simple part, and again, just keep in mind that it's both the equation of the curves, but also the range of the other variable that we're restricting. Okay, let's start with v equals 0. What do the transformations tell us to do? So let me come over here and let's just look at v is equal to 0. Well, plug in v is equal to 0 into both equations, and we've got to plot all of the points that satisfy the following equations. Well, u cosine of 0 and u sine of 0. Okay, cosine of 0 is 1, so this gives us u. And y sine of 0 is 0, so this gives us 0. So essentially, I just plot the equation x equals u and y equals 0. Okay, if y is equal to 0, I'm over here. Okay, and then x just goes from, what did we say, 1 to 2. Okay, so let's just put a little 1 and a 2. So I am going to plot this line. Okay, and this is the line y equals 0. Okay, and just I really want to emphasize, right? I'm looking at both the u values, but then u is equal to x. That's why I'm plotting 1 to 2 along the x-axis, but for the specific values that y are equal to 0. Cool. All right, what's next? So now let's look at the other curve. What was the other curve? The other curve was u equals 2. Plug u equals 2 into the two equations. I've got x is equal to 2 cosine of v. Y is equal to 2 sine of v. And now you got to think for a minute. What are these equations? What are the values of v? Well, v goes from 0 to pi over 4. Okay, and hopefully after a little bit of thinking, you recognize that, hey, wait a minute, these are just the parametric equations for a circle. And because I'm only looking at v's going from 0 to pi over 4, these are going to be a circle of radius 2 because of the 2's in front. Okay, so what I'm going to do is I'm going to try my best to draw a little circle here. Radius 2. And I'm only going to draw the curve. Let me actually, there's pi over 4 to help me here. Sorry, I don't want to use those variables. Okay, so I'm going to draw this arc right here. All right, and then you can kind of convince yourself that we're going to get a couple other curves, right? So if we look at this curve up here would be v is constant, pi over 4. We are going to get the following, okay? V is pi over 4. we're going to get this. This one's a little bit tougher to visualize, but just pause the video and convince yourself that that's true. And then the last curve, u equals 1. This is going to give us another arc of the circle, but the circle has arc radius 1. Okay, so the idea is we can come up with equations for all of these. And this is what we're going to get for our domain D in the blue plane. Okay, so D star is the rectangle, and D is this piece of an annulus. Okay, now the trick is, well, how do these distort? So that's not obvious. Of course, you can look at the argument that we used when we did polar coordinates, but I want to kind of go back to this determinant calculation. So let's go back and kind of think about, remember, this is x and this is y. We can take partial derivatives, okay, and you can kind of see I've got the calculation started for us here. X, what's the partial derivative of x with respect to u? Well, cosine of v is constant, so I'm just going to get cosine of v. What's the partial derivative of x with respect to v? The u is constant, but derivative of cosine is negative sine, so I pick up a negative sine v. Then looking at the y function, what's the partial derivative of y with respect to u? That is sine of v. And the partial derivative of y with respect to v is going to be u cosine of v. Okay, so what do we do with the determinant? Remember, multiply the diagonals and subtract the off diagonals. So we are going to get u cosine of squared v minus a negative u sine squared v. And the double minus signs turn into addition. So if I factor out the u and then add, I've got cosine squared v plus sine squared v. And what do we know? Time to make Pythagoras happy. This simplifies to 1. So I've got that the distortion factor is going to be u, okay, which is kind of weird. And you do have to kind of trust me on this determinant thing for now. Well, let's go back to this kind of key point since we're essentially done with this example. I said, okay, this is really just rebranded polar coordinates, where the u is just the r and the v is just the theta. Okay, so that's great. And if you remember, if u is equal to r, and we got that the distortion factor is u here, using this determinant calculation, this is just r, which is what we kind of argued geometrically in the past. Cool. All right, so this leads us to the next page here. So now we're in a position where we can state the full change of variables formula. Okay, again, one of the most important theorem in all of calculus. So the change of variables formula. So we're going to state it first in 2 dimensions. Okay, so at this point, just a quick review of our key terms. D is in the xy plane. This is the blue shape. Okay, xy plane. Then we've also got this D star also in the plane, but we're going to think of this as being in the UV plane. Okay, we also have some sort of transformation, a mapping. Okay, and first technical requirement, let's make sure that this is C1. What that tells us is that the functions x that depend on u and v, the functions y that depend on u and v, those are basically, they have partial derivatives, and those partial derivatives are continuous. We talked about the requirements on one-to-one and what those meant, but those are another more of our technical requirements. Okay, the other thing, make sure that the restriction of the transformation to D star, if I send all of those points mapped via T, it gives me precisely the map D. All right, well, given that, the change of variables formula tells us exactly how to, yes, you guessed it, change variables. Okay, so here it is. Let's box it. Okay, so what it's basically saying is as follows. So we've got the original variables, so let's call them OG variables on the left side. And this is an integral that we basically can't compute, or it's really, really annoying to compute it as stated. So the idea of the change of variables is, okay, this other side here is, you can see that this is going to be an integral in the u and v variables. Notice I'm integrating also over something called d star, which lives in the u and v plane. Okay, and the way we do it is, well, we use the transformation t to replace x with functions of u and v, y with functions of u and v. So technically, if you kind of want to think of it this way, you can think of what we're doing is we're doing f evaluated at t, which is evaluated at u and v. So that is using function composition here. Okay, and the part that's really surprising is, well, we don't just have just du dv, we have this extra piece here, which, let me highlight it a few times so it pops out, called jac t. Okay, and then we've also got some absolute values. So this is new. What is this thing? So this is called the Jacobian determinant of the map T, most often just called the Jacobian of T. And well, here is the definition. We are going to take the absolute values, so that's what those red absolute value lines are. We're going to take the absolute values of the determinant of a matrix of partial derivatives. Okay, so that's a lot of words, right? Absolute value, and in fact I have them down here, of a determinant of a matrix of partial derivatives. Okay, and what matrix? Well, this one. Okay, and there's actually two correct ways to write this. So the way I like writing it, and most textbooks have, is look at your first function x, take the partial derivatives with respect to u and v. Then take your second function y, take two new partial derivatives, and you put those along two different rows of a matrix. Okay, so a matrix here is just a little box where we've got four functions inside of the round parentheses. All right, now I'll remind you guys that the determinant of a 2 by 2 matrix is just AD minus BC, so I used that earlier, where you just multiply the diagonals and you subtract the what we call off diagonals. Okay, so this is the change of variables theorem. I've been trying to motivate why you shouldn't be too surprised that there's going to be this extra function that's called the distortion factor. So this Jacobian thing is the distortion factor. Okay, great. So that, first of all, just getting to this point is a fantastic accomplishment that you have seen the statement of the change of variables formula. Okay, so for this first part, I am just going to give you a derivation of why that formula is true, and then I will come back in a second part. Okay, so there's actually, I guess I got these two little remarks down here, or at the top of the video, remarks. Number one, super important result. I've set that at the top here. This is why we're going through this so carefully. It's really kind of the transition point where in Calc 1, 2, and even Calc 3 up to this point, we've really just been doing calculation. But what separates, your future coursework is, well, you're going to need to tackle with much more abstract key terms and deal with more concepts rather than just like, okay, here's another partial derivative you have to take, or here's an integration by parts where you kind of know what to do and you just calculate. No, we're more interested in just understanding concepts here. The other thing that's really important that we are kind of ignoring is orientation. Okay, I'll talk about this a little bit in some of the examples below, but this is going to be an important concept in chapter 16. So just kind of stay tuned. All right, so what is the geometry of the Jacobian? So starting first with, if I look at just the constant function 1, the change of variables formula tells us, right? So if we start with the area of a domain D, we can write that using a double integral. So just integrate the function 1 over the domain D using the x and y coordinates. So this says, okay, if I have a transformation T that basically tells me how to transform between those two shapes, as long as I integrate not just du dv, but the Jacobian, well, these are going to give me the same calculation again. And this distortion factor is basically making sure that if lines are getting stretched, well, that stretches it back so that basically the two shapes have exactly the same area. Okay, another way to kind of think about this is, well, I've got this right here. What is this saying? Well, on the left-hand side, this is kind of an interesting way of phrasing it. And I've got the picture here, where if I've imagined the area of the image under T of a rectangle in the UV plane, okay, what is the rectangle in the UV plane? Well, here it is. What is the area of a rectangle in the UV plane? Well, it's just du times dv. So the Jacobian basically tells us what to multiply so that, again, because hopefully with this picture you can see that these are not the same shape and they're not exactly the same area. So how much do I need to multiply the UV rectangle so that the area in the blue is exactly the same? That's what the Jacobian does. Okay, what's kind of interesting, I've got a little danger curve here, right? So this is not really correct, right? Notice that this dx dy is curvy, because again, I'm kind of abusing notation here, but hopefully with all the stuff we've been talking about, that makes sense. And the idea is, I've been kind of thinking about this as I was writing up the lecture notes for you guys. I was thinking, there's got to be a good term that's just waiting to be picked here called parallelogram, right? Because we've got parallelogram on the left, and this is almost a parallelogram, again, because we imagine that they're tiny, but they're curved. So, I don't know. What do you think? Do you like it? Let me know if you like that new key term. All right. So here is a very quick explanation for why the theorem is true. So I really like this quick explanation. So let's look at the picture here. If I vectorize this, so there's kind of a lot of details that I'm suppressing here. Well, first, take 2 points in, 2 points, 2 different values of u. I can build a vector I'm going to call it du. Do the same thing, but with dv, okay? Essentially, on the parallelo curve, this gets sent to 2 vectors over here, or sorry, 2 curves. Okay, and the idea is, well, we've seen how to compute the areas of vectors. Okay, so the area of this blue part is approximately equal to the area of the parallelogram formed by A and B. Now, what are A and B? I hope the picture is suggestive. Those are just tangent vectors to curves. Right, so if you kind of think of these as curves in the plane, I can take their derivatives and those are going to be tangent vectors. Okay, there's one of them, and I can do the one over here, take the derivative of that, gives me a tangent vector. And if you remember that really, these aren't surfaces, right? Because I'm actually in the plane, but if you, oh gosh, draw it a little bit better here. Okay, this orange parallelogram, actually a parallelogram, is going to be a pretty good approximation, provided all of these things are tiny, for the area of the blue parallel curve. Okay, so that's essentially the deep insight. Now, of course, what we'll do is, well, how do we calculate areas of parallelograms? Well, we'll use the cross product. Okay, now you might be thinking, hey, wait a minute. Cross products, I need vectors in 3 dimensions. These are vectors in 2 dimensions. And you are correct. However, I'll explain in more details why that's totally fine. Okay, so that's the quick explanation. Now let's do the more involved explanation, but it's the same idea here. Okay, now A and B are not the tangent vectors, right? So actually, let me draw the tangent vectors just here. They're going to be slightly different. Okay, so the quick explanation was that we are going to calculate the area of a slightly different parallelogram. But again, these should all be pretty close. Now, okay, let's go through A carefully here, where what I've got is I'm going to start at a point here. Okay, and A will just be the difference between those two endpoints. Essentially, the difference between the endpoints. So actually, let me do this. So we're going to start off at a point UV over here. And the V's are going to be exactly the same, but this will move a little bit. So I'll call it U delta U, comma, V. Okay, and then here, what are these going to be? Well, this is going to be T of UV, right? T sends that point over here. Okay, and then T sends this point over there. So what is this point going to be? This is going to be T of U plus delta U, comma, V. All right, and then because, again, I'm thinking of these as vectors, I'm just going to subtract them. And let's just kind of look at this derivation here together. Okay, so what is T tell us to do to these two things in the UV plane? Well, it's X evaluated at those two numbers and Y evaluated at those two numbers. Okay, and then I'm doing T evaluated at U and V, same idea, X and Y, but this time at U and V. Keep in mind these are vectors, so pointy brackets. Okay, so which says, okay, I can exploit vector arithmetic. All right, but before I do that, I'll just do a quick little clever trick here. Multiply and divide by delta U, which of course we're assuming is not 0 for these pictures to make sense. Okay, and then when we do the vector arithmetic, I've got pointy brackets in red. I'm going to keep this du outside, but the other du is going to go inside, and I've got essentially these two expressions. Okay, and again, these are just directly from the vector arithmetic properties, and remember that if I've got a scalar and I multiply a vector by a scalar, I have to multiply both components, which is why the du actually shows up in every single piece here. All right, now looking at those carefully, you're like, those look suspiciously like difference quotients. And you'd be correct, those are difference quotients. And in fact, because we kept the v variable fixed, these are essentially partial derivatives. Now I put squiggly equals because these are not tangent vectors, but they're really, really close to the tangent vectors. And a cool little remark here is we can actually make this more rigorous if we appeal to the mean value theorem, but I won't go into those details in this video. Just ask me either during office hours if you're curious. Okay, so what that gives us is we can say that A is approximately equal to this vector, which again, looking at this more carefully, you're like, hey, wait a minute. That is just the derivatives with respect to u. Okay, going back to kind of our little picture, let me draw a little tiny version of this. This is where basically v is constant, so I'm looking at this curve right here. Okay, and then basically this tangent vector is approximately the vector a. Okay, now this what does the du do? Well, generally, our parameterizations, let me draw this again. The vector is quite long. Multiplying by du basically shrinks it so that it's the appropriate size. Okay, now we can do the same argument with b, where basically pretend that the u is constant and the v's are varying. You're going to get a tangent vector this way, and then multiplying that by delta v kind of shrinks it so that it's an appropriate size. So all that's left is to calculate the area of the parallelogram formed by these two vectors that we just came up with, and then here's the trick. If I want to use the cross product as my tool, well, I do need vectors in 3 dimensions, but I can just kind of put them into 3 dimensions by putting little zeros in the third coordinate. Okay, and notice a little sneaky trick here. When I did this cross product, I actually factored out the delta u and delta v again, because those are, we can take those to be positive scalars in this context, and scalars just factor out of vectors, and it factors out of the magnitude calculation. All right, and looking at this, I noticed there's a small typo. Man, I can't eliminate typos everywhere. Okay, very tiny typo. Delta u, delta v. Here, and also here. Okay, but it somehow magically shows up at the very end here. All right, you can see I was distracted by just doing the cross product calculation, which by now we should be pretty comfortable with this, right? Here's our first vector, put that into the second row. Here's our second vector, put that into the second row. We need the formalism of the ijk, because we do indeed get a vector here, but just convince yourself that the first two are 0, and only the last one is really important here in the k component, where we've got, again, cross product. There's the cross in its name. Okay, and this indeed is exactly the Jacobian formula. Okay, so xu yv minus xv yu. Cool. Okay, and notice that they're kind of in slightly different spots than how I wrote the change of variables formula, but again, the determinant is a very flexible tool here. All right, taking limits will give us the official differential form version. Okay, cool. So that is a great place to stop in this first part. Let me just leave it off with the beautiful change of variables formula. Thanks for watching.